Thank you. So yeah, I'm going to take you a bit out of direct crisis management again, due to the horizontal character of the exposure mapping data that we are providing with the GHSL. But nevertheless, this information is possibly, again, very relevant for all kinds of crisis-related applications, because with our data, we are also able to support the preparation of population and housing censuses. So I think this is probably clear to all of you that this is really the basis for any decision making, formulating, implementing, and monitoring policies, because it provides information about the entire population, about the housing stock, about the quality of living, etc., etc. So this is really baseline that is very relevant. It should be repeated every 10 years. I've shown here at the bottom right a map that illustrates for the 2020 census round how countries are implementing that. And you see already on the left-hand side this census timeline that we don't manage to get a census in all countries in 2020. We are already happy if we are getting all countries within a +5, -5 years time frame, but there's always countries that are for many reasons, political, financial, also disaster-related reasons. Also this time, the 2020 census round was heavily impacted by the COVID pandemic. So we have huge delays there. And this is where we are working together with UNFPA, the UN Population Fund, that tries to support countries doing that in getting countries up to speed. So let's have a look at how Earth observation data and information about settlements and population can help there. To understand that a bit better, I put here this slide to illustrate a bit the different steps of census implementation. So there's a long preparation phase, this pre-census operations, that starts actually with all the legal, administrative, and also financial commitments that are needed to set up the census. So it's really one of the biggest exercises that the country is performing. So consequently, it really takes more than 5 years to usually prepare a census. After then this legal administrative framework is set, then the questions need to be designed, and also what is very important, the cartography and the delineation of the census, because most of the time there's really people sent into the field to talk to each and every single household. So they need to understand where are we going. Then it has to be assured that these areas are not so big that one enumerator can do his part within a certain time frame. And this is really where we can then help already in the pre-census operations to support, and I will show 2 examples of how we have been doing that, or how this could happen. Then the actual census happens, so enumerators go to the field and talk to the people, understand their living conditions, etc. But that then needs to be also monitored. So did we really go to all the houses that we were planning to map? And this is then also in the post-census operations where we can support with the monitoring and evaluation using our data. And we have been doing this so far in 2 countries. In Papua New Guinea, this is the first example that I would like to bring. The last census there took place in 2011, and they were supposed to do the census in July 2020. And we were then also contacted by UNFPA asking, well, for Papua New Guinea, we basically have no information. There's no recent settlement map. Also, the population data they are having are heavily outdated. Can you support us? And we were then starting, but in the meantime, also this political process went on. So COVID started, then it was postponed to July 2021, and then they said, okay, no, we wait for the next elections, which are scheduled for next year. So this is just to show you a bit how this process is really depending on a lot of also political decisions. But to show you what we did is we were using Copernicus Sentinel-2 data, more than 10,000 tiles to cover the entire island. It's a tropical area, so heavily impacted also by cloud coverage. And this is where we then also reached out to Norway's International Climate and Forest Initiative that offers also planet data to complement then for cloudy areas. And we were then extracting the settlement information. You can see this on the bottom right picture for one of the settlements in the central area. And talking to the people in the field, they were really happy with already such very basic information that they did not have. So they had started really to send out people with GPS to map households. And even if they are doing then still some of those operations, such a map as we have been producing could really guide them a lot. I mentioned that then there was also quite some delay in the census itself. So UNFPA then started to come up with sort of a bottom-up census, pre-census. They wanted to have a most recent population grid to prepare better for the actual census operations taking place. And this is where then our built-up information was integrated to come up with a more recent population grid that then is basically now used to inform also the preparation of the next election, which then will be again the trigger for the actual census in 2020. So this was a very, very concrete example. We then, with the help of the European delegations, also reached out to other countries for interest, and we got feedback from South Africa. South Africa actually computed the census this year in February, so they contacted us basically in January. So everything was already set in place, and in any case, the preparations and the quality of the censuses in the past in South Africa is quite high. But nevertheless, South Africa said, look, we were not really fully exploiting the use of Earth observation in the census. So can you help us with the ex post analysis? So we share with you the past censuses and this enumeration areas. Please tell us how we can then maybe improve for the future. And I'll show you a bit some of those findings that we were getting. So having global data, of course, we can identify the built-up areas. And since we have also multi-temporal data, we were then able to really look at the changes between one census and the other. So on the left-hand side, you see the built-up change really at the pixel level that we were then aggregating at the municipality level to highlight those areas where we have the biggest change. And this is, of course, not to a big surprise. The biggest changes were happening in the Gauteng area with Johannesburg and Pretoria, the capital, so the industrial core of South Africa, where most of the activities are going on, but also in the coastal states, we see some of the changes. And then in the next step, we really zoomed into those areas. So you see here two examples of two small rural municipalities where then we could really look into the different areas. So this zoom in, I hope you see my mouse here, also shows built up that was newly created in an area that was basically before only one enumeration area. Then this enumeration area was split into two so that the enumerators had less work to do. And likewise, also another example on the right-hand side for this small municipality of Potchefstroom, where we also could point to those areas where the enumeration areas should be updated to a major built-up increase. So it's really to give you a quick overview of how such information can be used. So we are able to use directly the GHSL data to delineate enumeration areas, but also it can really help reducing the cost, because in the past, or the standard approach for census is you buy most recent VHR imagery for entire countries like South Africa. It's also really costly, but with our data, they can really point to those areas where major changes have been taking place. And they can also use this information then for checking the coverage of the field operations, and use information on the population disaggregation for estimation of population in hard to reach areas. And with that, I end my presentation. I'm happy to take questions if any arises. Thank you.
Thank you, Thomas. Indeed, I mean, the work that you show is something that is highly relevant, not only for EMS, but quite for a range of other policies as well. We'll see that later also in the policy session. So I don't see currently let me check, a question in Slido for you. So I would suggest we move on with the next presentation. And here it's really a great pleasure for me to introduce to you Viola Otieno from the Intergovernmental Authority on Development. And Viola will present us a use case on the East African Drought Watch. Viola, the floor is yours. We can see your slide. And let's see if we see also your camera. We cannot hear you yet.
Can you see my camera? Sorry.
Yes, we can hear you and we can see you now. Very good.
Okay. All right. Thank you so much. I'm very honored to join in this session to celebrate the 10 years of Copernicus Emergency Management Service. So I am in rural Uganda right now, so the internet is a bit shaky. Because of that, you will allow me to turn off my camera as I do my presentation.
Yes, sure, yes.
Okay. I've put in place several measures just to deal with the internet connection, and I'm hoping that works well. Let me just put my slide on presentation mode. Okay. So once again, my name is Viola Otieno. I'm an Earth observation expert at e-Geos Climate Prediction and Application Center. And as Peter mentioned, we will be showcasing the work we have done with JRC Drought Unit, and we are calling it the East Africa Drought Watch. So just brief introduction to ICPAC for those who do not know ICPAC. So ICPAC is based in Nairobi. It's a specialized institution of e-Geos. It was started in 1986 as Intergovernmental Authority on Drought and Development. And the reason I put this up is because you can see that as far back as 1986, drought was an issue in the region. And then ICPAC was established in 2003. So ICPAC is also a WMO designated regional climate center for Eastern Africa, and we serve 11 countries in Eastern Africa, and the countries are listed on the slide. The mode of operation is that we work very closely with national meteorological agencies and institutions. But in addition, because we also look at climate applications, we work closely with environment, disaster, and climate change institutions as well. Our services can be divided into 8: climate forecasting, climate change, agriculture and food security, disaster risk management, water resources, capacity building, and climate information, and also environmental monitoring. Okay, slide is stuck. Sorry, Peter, can you hear me?
Yes, we can hear you still. So indeed the slide is stuck.
Yes, it is stuck. I'm trying to, let me just share again and hopefully it works. Apologies for the connect. Okay, we're good. So the East Africa Drought Watch is a publicly available online system. It uses Earth observation data, but also weather information as well to monitor drought conditions. On the system, you're able to get automatic 10-day warnings for developing in actual droughts, but also for recovery of drought conditions as well. As mentioned, this is one of the services we have developed with the Joint Research Center, specifically the Drought Group of the Natural Disaster Risk Unit under the project CLINSA. And the service itself is hosted at eager Disaster Operations Center, which is a newly established state-of-the-art center, and I do not exaggerate when I say state-of-the-art, for providing regional multi-hazard monitoring and early warning to improve response in disaster risk. So a brief background on the current ongoing drought. Approximately 50 million people highly food insecure with very high risk of famine confirmed for parts of the region. More than 3.6 million livestock deaths have been reported. Thousands of wildlife animals have died as well, and hundreds of thousands of people have been displaced. And this is because we are facing 4 consecutive failed rainfall seasons. And the current season, October, November, December, also has a very high probability of failure. So if you look at the graph on the top right, you see that this is the longest drought period we've ever had. And also in terms of intensity is also quite severe. The impacts, of course, are not isolated. They're compounded by global events, also conflict and insecurity and other climatic events such as floods. So if you look at the bottom images, the image on the bottom right, you can see that you have areas experiencing very high exceptional heavy rainfall, yet at the same time, you also have areas that are in drought conditions as well. So the basis of what we do is, of course, convergence of evidence, but I think I'm preaching to the choir here because everyone in this room is probably aware of that. So it's based off the Global Drought Observatory and also the European Drought Observatory as well. And we're using vegetation conditions. We use FAPAR normally for this. We use soil moisture as well, and we also use SPI as well. When you talk about convergence of evidence, when you're producing reports and bulletins, we also look at other indicators or other impacts, such as displacement. We look at the reports that are being produced by the countries, and we also look at any news that we could get from social media as well. These are examples of the products that we produce. We have a periodic bulletin that is produced every month, and that is how it looks. So you have the drought conditions. We also provide information on the forecast, and then we also try to give some key messages and forecast and advisory as well. We also do national level analysis. So we've done quite a couple for Somalia because Somalia is of great interest to both the regional institutions and international institutions as well. And this is also made available to our users and partners as well. In terms of what is also available on the system is that you can have regional analysis, and this allows for transboundary coordination of response, but also transboundary coordination and monitoring as well. So on the very first thing you can get is the ranking in terms of geographic spread of the drought, but also the intensity as well. So for the 3rd decade of June, we had Uganda leading, and then South Sudan, Somalia as well. And then, as mentioned before, we try to look at the forecast as well, and we also try to look at other sources of information. So the map you see on the bottom right is from FuseNet, and this is the map showing the status of water points. So whether the water points are in good condition, or they are under watch, alert, or near dry, or seasonally dry as well. The other products you can get at national analysis, and this is feedback that we received from when we're dealing with the stakeholders. We showed them the regional analysis where you can see which country is the most affected. And they said it would be also interesting to have analysis, similar analysis for national level as well. So it means for every country, you can be able to tell which are the most affected regions or administrative levels within the country as well. Another product that is shown on the bottom right is the automated report that you can generate from the system. So this is available for any user who's using it online. You select a country, and then you're able to generate a report for that specific country. At national level, you can also do a time series map of the drought conditions, and you can also do a time series graph of drought conditions as well. And this we find particularly important in trying to understand the evolution of the drought. So the graph at the bottom shows you the percentage of the area under different levels of drought conditions, and then you have the time period as well. So for Uganda, you can see that we had a bit of a rainfall deficit around May 2020 to September 2020, and then a bit of recovery. And then once again in May 2021, we see a lot of the areas having a rainfall deficit and different drought conditions as well. The other thing that came from stakeholders as well is that, well, you can look at the national level, but for decision-making purposes, it's important to also allow for sub-national level analysis. So we have regional for transboundary issues, we have national, and then we have sub-national as well. So again, you can select a sub-national level, and then you can be able to do analysis. You can get the graph that shows you the evolution. We also do an estimate of population exposed under the different categories. And we also combine this with information from other systems as well. So the two graphs, NDVI and temperature, these graphs we're getting from the East Africa Agriculture Watch, but based on this, we're able then to generate the report. In terms of user statistics and success stories, so these are the numbers of people who have accessed the system and also the distribution as well. You can see that the distribution is almost all the countries in the world. So just a few of the great countries, that's where we've not had any users. In terms of the success stories, we got feedback that for the government of Somalia to announce a state of drought emergency last year, they used the system to kind of have an idea of the intensity and the areas that are affected as well. The system has also been adopted as a prototype for an adaptation funded project, which is called DRESS. We've received a lot of requests for collaboration with humanitarian agencies for information sharing and data sharing as well. We also received feedback that for the people based in the US, most of the time access was due to or to validate what kind of support to give to Ethiopia, but also where in Ethiopia to give the support as well, the response support. In terms of implementation, we adopted what we're calling the adopt and adapt approach. So e-Geos was founded as a drought institution, but until now, we did not have a system for monitoring and providing early warning information for drought. So we would use the indicators separately, but now we have an automated system that allows for that. It is based off the Global Drought Observatory. So this, you see that on the left, and then you see on the right what we have developed, the East Africa Drought Watch. We had to do some adaptation to the system, and below here, I show the adaptations that we did. So first was the interface. You can see that we modified the interface to use more modern technology. We also had to change the data as well. The first results that we received of the combined drought indicator, when we presented it to the stakeholders said, well, this does not quite reflect what is on the ground. So we had to come back and then do a bit of investigation, and we ended up replacing GPCC data with CHAPS data, and most of the stakeholders are now happy with the CHAPS data as well. That also means a higher spatial resolution. We also focused a lot on stakeholder engagement. So that means working very closely with drought management authorities in the member states, but also disaster coordination agencies as well. And this engagement include validation of the product, but also gathering user requirements. We also realized that we needed to support institutions in their workflows as well, just to promote acceptance and adoption of the system. And then there's one key point which comes out every time we have a meeting, and that is the harmonization of early warning messaging. So you have the member countries having their own drought systems for some of them, and you also have the humanitarian agencies having their own drought managing or monitoring systems. So the question is, how do we ensure that the message that is being sent across is harmonized? System optimization, we also changed from the language that was used to develop GDO to Python and Go languages, which are support more parallel processing and therefore making the system a bit faster. And then cascading dissemination in terms of interoperability. So the products available on East Africa Drought Watch are all available on GDO as well. So we have that kind of link. But East Africa Hazards Watch as well. So what is the future? I think for us, the future is a lot of collaboration. So we welcome a lot of collaboration, but we're also working towards impact-based focusing for early warning and, for early action and anticipatory action as well. During one of the meetings, we asked the focal points from the countries, what was the problem with this drought situation? And they said early warning is no longer a problem, it's the early action. So we're working towards linking early warning information and early action or anticipatory action through the impact-based focusing approach. And that's also the reason why I'm in Uganda as well, meeting with stakeholders. We're also working towards the WMO ambitious goal of having everyone on the planet covered by multi-hazard early warning systems in 5 years. So in our small way for the Eastern Africa region, we're trying to develop multi-hazard early warning systems. We continue to develop the capacity of member states to generate, but also to be able to utilize the early warning information that is available. And we are also enhancing the capacity of the IGAD Disaster Operations Center to support regional multi-hazard monitoring and early warning, and that means end-to-end early warning system for the Eastern Africa region. So on the bottom right, I have put some of the links for the organization. We have the organization website, but also some of the other systems that we have developed that heavily rely on satellite data, satellite data, Earth observation data. And that is the end of my presentation. I hand over back to you, Peter, and I welcome any questions or comments.
Thanks, Viola. Thanks also for staying on time. The internet connection worked perfect, so that was very good. Now this is really, I mean, is really I find a very great example of not only usage of products through EMS, but actually even more a knowledge transfer of building up a regional system based on some of the aspects that we have in the Global Drought Observatory. So I think this is really a nice example of this way of fostering these types of applications also at the regional level. So thanks a lot. I also think that one of the topics that you have mentioned there on the anticipatory action will come back in the follow-up presentation, and not right now, but the one after. We have, I see, one question, and that relates to the plans to expand this type of systems. Are there any plans, Viola, to expand this type of system to other areas in Africa as well?
Thank you very much for the question and also the feedback on the presentation as well. In terms of plans to expand, I mentioned that at IGAD, we have IGAD Disaster Operations Center, and there are 3 similar disaster operations centers in the continent. So one is based at Africa Union, and the other one is based in an organization, ACMAD, in Niger, West Africa. So the 2 institutions, seeing that their mandate is continental level, I know for sure that ACMAD is working at implementing the drought watch at a continental level as well. So those are the 2 main areas which I am sure of about the expansion of this system. Thank you.
Okay, thanks a lot, Viola. Thanks again. I think we have to move on. I just remind everybody that please continue to submit questions. We will try also to answer them directly in the Slido. Now, let's move on to the next presentation. And here we have Luzietti from e-Geos, one of our service providers for rapid mapping. And Lucia will present us a couple of use cases, very prominent use cases that we dealt with in the rapid mapping component in the previous couple of months or years. Lucia, the floor is yours.
Thank you. Good morning, everybody. I have the honor today to represent the service provider of the rapid mapping component, the industrial team that is providing the service with continuity since the beginning of the operational phase 10 years ago. I'm the technical coordinator of the rapid mapping team and part of the on-duty operator team that received new requests from the European Response Coordination Center, collect a requirement directly from the authorizer user or the end user when available of the service, and define in few hours the rapid mapping production plan in order to satisfy the user needs. Despite the rapid mapping service is characterized by a strong standardization of the products, let me underline that each activation requires an adaptation of the operational workflow of the products due to the specific needs of the user. And today I will show two excellent examples of past rapid mapping activation. So, as mentioned, as already showed this morning, the rapid mapping service is the fastest mapping component that can react after a specific request from the user, providing information of the extent and the impact of the event. In 10 years, the service collected 637 activation and worked in more than 100 countries. What is new and it's ongoing now in the rapid mapping service, it's a new activation for flood in Australia that we received yesterday. This morning, the first SAR imagery were acquired, and we are now in the phase of the preparation of the reference data, waiting for the availability of the SAR acquisition for starting the flood analysis. So the first use case that I'm going to show you is the volcano eruption in La Palma. It was an exceptional rapid mapping activation, as already mentioned this morning, for the high number of products delivered to the user and the long monitoring of the evolution of the lava flow. It was also an example of the great cooperation with the user that supported us during the wall activation, providing relevant information from the field and updated us also on the needs in the different phase of the emergency. Indeed, the request of the user at the beginning of the event were completely different with respect to the final monitoring that we delivered in the final phase of the emergency. In this slide, there is the standard workflow of the rapid mapping service. For this specific activation, we received in the afternoon, in the evening, the request after 4 hours from the volcano eruption in La Palma Island. And we start immediately to understand the best product to deliver to the user needs, the definition of the area of interest, and the request of the first satellite pass through ESA. The day after, we were able to receive the first SAR imagery, the first acquisition over the area of interest defined with the user that was essential to provide the user with a first delineation of the lava flow. In this slide, you can see a picture of the first SAR acquisition used for the analysis. It was a Cosmos CEMS second generation. And at the end, the user received the notification of the availability of the first product about 33 hours after the triggering of the rapid mapping service. It's interesting to underline that in this activation, the first requirement of the user was to receive frequently an update of the evolution of the lava flow, because the first monitored products were relevant for a first estimation of the velocity of the lava flow front. And so for this reason, the first monitored product were delivered 12 hours after the first product. And in this picture, we can see the different SAR acquisition used. The first product was based on a simple, a single SAR acquisition, but starting from the second product, we started to base the analysis on multi-temporal coherence analysis based on SAR acquisition, because we were able to receive interferometric imagery. So this is the evolution after the third delivered product, and again here the needs to collect very close to the beginning of the event more imagery, also because the first picture of the extent of the lava flow were used for modeling the evolution of the event, identifying different emergency scenarios. So in order to understand the potential impacted area due to the evolution of the lava flow. The analysis was based also on optical, very high resolution optical imagery when suitable for the analysis. Indeed, it was very difficult to acquire good optical imagery due to the cloud coverage, due to the smoke, especially during the first week after the volcano eruption. As mentioned before, it was also a great example of cooperation with the user, because during this long activation, we had the opportunity to have teleconference with end user in the field that provided also additional data that were integrated in the rapid mapping product, like the ash deposit thickness that was provided by the end user. And so in this picture, there is a view of the of one of the last product where also this information was integrated. During the activation, additional requests were collected from the user, for example, the identification of the location of the event. And so also this information was integrated in the product and updated thanks to the availability of new satellite acquisition. So at the end, 64 was the record-breaking number of damage-grading products that the rapid mapping team delivered in 90 days. It was the first time that the rapid mapping team worked in a so long monitoring, 3 months of monitoring over the same event. The more than 1,000 hectares was the extent, the landscape that was covered by the lava flow. We started delivering the first product where we extracted the extent of the lava flow that was only 100 hectares, and about 3,000 number of buildings were completely destroyed, and more than 19 kilometers of roads infrastructure again were completely destroyed. During the whole emergency, more than 7,000 people were forced to evacuate their homes, and so these are the the very impressive number of these activation. At the end, the Copernicus Emergency Management Service received a Medal of Merit by Spanish Civil Protection, and it was a pleasure to be part of the team that worked on this activation. Now I would like to show you a completely different activation, similar to the activation that is now ongoing in support of the Australian authority. It is again a past activation that we where we worked in July this year for where the Australian authorities triggered the rapid mapping service for a huge flood in the New South Wales due to prolonged heavy rain. Again, here there is a picture of the typical workflow. So we received the activation several hours after the beginning of the event. During the first hours, we defined the first 3 areas of interest with the user, and we collected all the details to define the rapid mapping production plan. We submitted the request of data, and we were able again to deliver the first product to the user 34 hours after the reception of the rapid mapping request. In this picture, there is an example of the rapid mapping product delivered to the user. In this case, the user was interested in the monitoring of the extent of the flood. So for this reason, were delivered only delineation product based on SAR data due to the very bad weather forecast. This is another example of the possibility to update the status and extent of the flood over a specific area. It's clearly visible in this product, the evolution of the flood extent after, in this case, 24 hours. Again, it was a very excellent cooperation with the user. It's essential during the whole activation to collect feedback from the user and to understand if something has to be improved or the requirement change because change completely the needs due to the evolution of the emergency. In this specific case, the user, after triggering the service at the beginning over only 3 areas of interest, due to the evolution and the very huge impact over other area, decided to add 1 additional area after few days, and then 2 additional areas of interest. And in this picture at the end, there is a view that is reported in general in the activation extent map of the area covered by the rapid mapping analysis. So we worked over 6 areas of interest, delivering at the end 19 rapid mapping product due to, again, the delivering of several monitoring over all the area of interest. And at the end, we produced 43 ready-to-print maps. This is an extract of the feedback form received from the Australian authorized user that was grateful for the service that the Copernicus CMS provided. And yes, this is the final step of a rapid mapping activation, the collection of feedback from the user that let us underline that are essential for continuing to improve the service that we are delivering to the user. So thank you very much for giving me this opportunity to join this section. Thank you.
Thanks a lot, Lucia. Indeed, I mean, as I said already this morning, I think you, the service providers of the emergency management service, are a fundamental and crucial part of the success of the service. So again, thanks to all of you, not only the ones from Rapid Mapping, but all others as well. Really, yeah, I think the recent examples that you've shown really clearly highlight also the capabilities that we have now at hand with the Rapid Mapping service, covering, you know, not the usual one. Everybody said, okay, floods, you know, it's fine. But I mean, in particular, the lava flow monitoring, I think, was really a big challenge, and is something that is also hard to prepare, because typically there's not so many luckily there's not so many volcano eruptions, at least in Europe. So really I think yeah, a nice use cases of the emergency management service products. Let me check. I have not seen. There's another question for. We'll go back to Thomas at the end of the session. But for you at the moment, I don't see a question. So we'll move on to the next presenter. Thanks again, Lucia. Now the next presenter is Liz Stevens. Liz Stevens has actually, I think today you have two hats on, right? From the University of Reading, as well as the Red Cross, Red Crescent Climate Center. And Liz will present on global flood forecasting for anticipatory humanitarian action, something that was already mentioned by Viola beforehand. So Liz, the floor is yours.
Yeah, thank you very much, Peter. Yeah, as Peter introduced me, I have a joint position at the University of Reading between the Red Cross Red Crescent Climate Centre, and I'm actually presenting with both hats on today. If I give an opinion, then it's my university hat, and if it's not an opinion, then you can call that the Red Cross. So just to start off with, just to tell you a little bit about anticipatory action. In the humanitarian community as a whole, this has grown to, well, over 52 countries now, all over the world, and multi-hazard as well. But I'm just going to be talking about the flood side. Actually, my colleague from the Climate Centre, Dr. Gigma, will be presenting tomorrow on aspects more broadly. When it comes to using forecasts, there are several challenges related to their use. So within the humanitarian community, we have a window of opportunity for taking action, and that's the sort of overlap between the time needed to take the actions and the lead time at which those forecasts have skill. And of course, we're using probabilistic forecasts as well, so there is a lot of opportunity for confusion to come in. So within the Climate Centre, we are trying to undertake research to really be able to support the robust use of those forecasts. Because of course there are limited humanitarian resources, and we need to make sure that when we are allocating them for early action, that they're being allocated in a robust way. The way that we do that within the Red Cross Red Crescent movement is that we use early action protocols, which provide those plans in advance with evidence behind them to support that those plans are robust. And when it comes to the forecast triggers, we need to generate evidence that those forecasts are skillful. So in an ideal situation, we would be using the local forecasting capacity, and they might have archive forecasts and good observational data so that we could do that evaluation. But of course, in many of the countries where we're working, that isn't the case. So more realistically, because that task is so resource intensive, we're often relying on reforecast data sets from global producing centres, and the Global Flood Awareness System is of course one of those. So the GLOFASS, the Global Flood Awareness System web interface, does provide some information on forecast skill, but what we have discovered by looking at this is that it's not necessarily useful for our own decision making. So here is an assessment for Uganda. So on the left is the web interface, and darker colours show you where the forecast skill is available or is better for longer lead times. And on the right, we've undertaken a decision relevant skill assessment against gauge data. So the left one isn't gauge data. And the crosses show actually where GLOFASS is not good enough for our decisions. So you can see that actually there is a bit of a mismatch between the two. So we need to do that extra work to really make sure that we're using forecasts robustly for the allocation of funds. And so what we can actually do is go into much more detail than that even. And in this scenario here, undertaken by a PhD researcher, Sazad Hussain, who comes from the Flood Forecasting and Warning Center in Bangladesh. He has done some work to look at all of the different decisions that are being made by different organizations that want to take action before a flood. So this is for the Brahmaputra River in Bangladesh. So you can see things like evacuation, agriculture decisions, internal decision-making within the government, as well as humanitarian operations as well. And what we've been working on is to think a little bit beyond just understanding what threshold creates an impact and how far in advance of the flood you need to act, but also thinking about the acceptability criteria for forecast skill. So for example, we look at things like the acceptable delay until flood peak, until the flood peak. So what this means is that actually, if a flood arrives a lot later than was forecasted, is this a problem for the decisions that were being made? Now, in the case of things like evacuation, that is a problem because we don't want to remove people too early, especially when their livelihoods depend on the floodplain. But in the case of humanitarian operations, it doesn't really matter if the flood arrives a little bit later, if we've been undertaking cash assistance, for example. There are then decision criteria related to what is acceptable in terms of false alarm ratios and what is acceptable in terms of the probability of detection. Now, you can imagine if you were a reservoir operator somewhere in Europe, you could be able to do a cost-benefit analysis and come up with some very precise answers for that. But in general, when we're looking at these kind of decisions that are being taken here, this is sort of done in consultation over what is acceptable, because it's, of course, impossible really to put a cost on some of these decisions. So then when we actually undertake the evaluation against these skill criteria, we end up getting some rather counterintuitive results. So on the left, you can see that you've got a grey box, which is actually quite small in terms of, gives us the sort of accepted range for probability of detection and the false alarm ratio. And on the right, a larger box, and actually the forecasts end up being inside that grey box. So what this tells us is that GLOFASS can be used for longer lead times for the communication for flood preparedness and response, but not for the shorter lead times, which is for evacuation. So this is rather counterintuitive. Normally we say that the forecast skill is better at the shorter lead times and not for the longer lead times, but because the skill criteria are more strict at that shorter lead times for the decisions that are being made, we end up with these counterintuitive results. So the second challenge when it comes to using those forecasts is what to do in data poor settings. So of course, in many of the places of the world where we want to work, there aren't those kind of gauged river data sets. And so we've been looking at using disaster impact data sets for evaluation. So the plot on the right is going to show probability of detection. And what we've done is undertake a skill assessment for some rivers in Kenya and Uganda. And we've evaluated the model, first of all, using the river gauge data. So this is in locations where we had it. And then we've rerun that evaluation using the impact observations. So ideally, we don't want to see a difference in that probability of detection between those two data sets. But we can look at what the difference actually is. So for these rivers, we actually see that the two are quite close together. So there's only about 0.3 difference maximum in those locations. So what that's telling us is that the impact data does seem to give a reasonably similar assessment of GLOFASS skill than using gauge data sets. But it does hint that the probability of detection is lower in when we assess it using the impact data, which we think is because actually those impact data sets are aggregated often to larger scale than just the particular town, for example. And so they capture lots more information about flooding other than just the floods on the major rivers, so things like pluvial and flash floods. So what this is telling us is that if we only used impact data, we might actually end up throwing out a forecast that is actually good enough. But really, I think this is quite promising for those locations where we don't have gauge data to give us some indication of the robustness of the forecast. And then the third challenge is how we can use unverified models in times of imminent crisis. So in the first two challenges I was talking about, where we have the opportunity to do evaluation in advance to give us confidence in using the models, but often we're acting in locations where there's a sudden disaster and we really need to be able to use GLOFASS during that time, even if we don't have any background information on its skill. So we at the University of Reading and the Climate Centre now are producing flood forecast bulletins for the UK government, and we've been doing that since Tropical Cyclone Idai in 2019. And we're often required to give that expert assessment in locations where there are no other forecasts available. So there really is an advantage to the GLOFASS approach, because when we know the model climatology, it provides us with a reference point to be able to give some kind of assessment of what the likely flooding will be. And we've designed procedures and protocols with a careful use of terminology and phrasing so that we can navigate that uncertainty. And also, I'd say that the contextual information is really important as well. So, for example, there were lots of tropical cyclones in southern Africa early this year, and the GLOFASS web interface provides us with an opportunity to look through historical forecasts. So we can look back for what was being forecasted for Idai in 2019, and then for Anna in 2022, and Gombe in 2022. This is for the Likungo River in Mozambique. And we can start to get a feel for what is different between each of those events. And that provides that contextual information for partners on the ground so that we can say, flooding in this river is likely to be more severe than it was for Tropical Cyclone Idai, for example. And just to give you a more recent example again, this is for a comparison of Hurricane Iota in Central America and Hurricane Julia, which made landfall earlier this week in Central America. And we were able to provide information here to say, again, that the flooding was not likely to be as severe as from Iota, but would still be quite major flooding across the region. So in summary, current off-the-shelf assessments of forecast skills, so those that are appearing on the web interface, are not that helpful for ensuring robust decisions, but a lot of those reforecast data sets, everything that comes behind it, can be used by us to really assess that forecast skill. That decision-making context is also a really important consideration and often ends up with very counterintuitive results, as I showed. And we have been working towards using impact databases in data poor settings, which we have to use with caution. And I expect there are people on the webinar today who are also working on various databases which we could use to do that evaluation with as well. And again, sometimes unverified models will need to be used, and that contextual information is really important. And I think the web interface is very good for that, but there could be a lot more integration of monitoring and mapping to really help us with those decisions and with the communication of what's likely to happen. Thank you.